Gracias. Can you hear me okay? It's working all right? Okay. It's a tremendous pleasure for me to be here in Villahermosa. We've had a wonderful time. I've met many extremely enthusiastic young students learning physics. I've had some very good meals, a very nice time. And I'm happy to be here to talk to you a little bit about the sort of research that I'm doing. Most of my talk will be about some things which I'm doing in a more modern way over the last 10 or 15 years. But the organizers have asked me at least to mention the Bose-Einstein condensate, for which maybe I'm best known. I'll talk about the Bose-Einstein condensation, which occurred first in 1995. What's been going on now in these 23, 24 years ever since? I'm talking about extraordinarily low temperatures. In physics and in chemistry, we like to measure temperatures from absolute zero. So here on Earth, outside today, in Kelvin, it's about 300 degrees. In Fahrenheit, 81, I don't know, 29 outside right now. It feels warm. And then gradually it gets colder and colder. As we get down closer and closer to absolute zero, we're at extremely low temperatures, but we still measure them in positive numbers. This number, 3 degrees Kelvin, is an interesting number because it's the lowest possible temperature you can get to without intervention by an intelligent species like humans, because this is the temperature of deep space. But for us, 3 degrees Kelvin is really a very modest temperature, not so high at all, not so low at all. We go much lower than that. We'll start with this temperature, 3 degrees Kelvin, and that is up here, 3 degrees Kelvin, something like the height of Mount Everest. We are going down to temperatures which we measure in billionths of a degree above absolute zero. So the temperatures we're going to are just a few hundred billionths of a degree above absolute zero. It's like comparing Mount Everest to the thickness of a pencil, something like this. We get to these extremely low temperatures using lasers, and it's counterintuitive. It seems strange to us to imagine that we could get to low temperatures using lasers, which we think is something that we use for burning things, but it works. And then additionally, we put the atoms into a magnetic trap, and we evaporate from there. We get to very low temperatures. These are pictures of condensates which were taken back in 1995. For us, this is a relatively high temperature, 400 billionths of a degree, so less than 1 billionth of a degree above absolute zero. We get colder, this thing appears, this is the Bose-Einstein condensate. You can think of it as many thousands of atoms all participating in exactly the same quantum wave. This is the Bose-Einstein condensate. And this is really where things were in 1995. Since then, more than 1,000 people have worked in this area. Maybe 10,000 papers have been written, something like this, and we should ask where has it led? And the answer is many places. I can't really review it all for you, but I'll mention some more slightly practical implications. Let's see. One is in this direction of quantum computing. This picture here, you can't see the label up above, but it's 25 individual atoms which are trapped. And you can think of each individual atom as being like a bit in a computer, a bit which could be 0 or 1. When there's something as small as atoms, they could be 0, or instead of 0 or 1, they could be 0 and 1 at the same time. This is a hint to the power of quantum computing. Many different groups, companies, universities are working to try to build a quantum computer, and no one can be sure what the ultimately successful thing will look like. But one thing we can be very sure is that surely a quantum computer, if it ever works, will have to be kept extremely cold. And so, I don't know if anyone still recognizes this, but this is an old-fashioned machine for making ice cream, as it was made many years ago. You put ice here, and inside you put cream and sugar, and we can think of this. This is my favorite flavor. It's strawberry ice cream. And we can think of that as where the cold bits of 0, 1 could be, and then floating around it could be Bose-Einstein condensation. So a very likely direction for the future of Bose-Einstein condensation is as the fluid inside your air conditioner, the Freon, whatever it is that's cooling your condensate, keeping it very cold. Bose-Einstein condensation is also relevant to the technology and science of very small machines. This is a fantasy, a cartoon, but it's an idea of something that looks a little bit like a car made of individual molecules. Very exotic new materials with amazing electronic and magnetic materials, electronic properties made, devised from very tiny objects. Basically, what we understand is that the future of technology is in the direction of the very, very small, whether we're talking about atoms, whether we're talking about electronics, motors. This is supposed to remind you of an electronic circuit. These are electrons, they come along, they come to transistors, they go this way, maybe they go this way. As things get colder and colder, they act less and less like, as they get smaller and smaller, you think of them less as little particles and more as waves. So imagine these waves are going through your transistors, and when they come through, as waves do, they can interfere. And you can get basically quantum interference between these waves. To understand these things, we need to understand the physics of quantum mechanics very carefully. And to do that, I think, what does this have to do with Bose-Einstein condensation? Is a Bose-Einstein condensation very small? No. Actually, Bose-Einstein condensation is relatively large, perhaps a millimeter on the side. But basically, the effect of ultra-cold, the very, very low temperature of Bose-Einstein condensation makes quantum mechanics big and easy to see and understand it. So we can understand and design very, very small things. So where is Bose-Einstein condensation these days? You can think of it as a very high-tech air conditioning unit for a quantum computer. You can think of it as a teaching lab for a generation of scientists to more deeply understand the quantum mechanics, the science of the very, very small. And I haven't talked about this, but it's possible to use for precision sensing of acceleration and rotation. I wonder if it's possible to turn down the gain on my microphone, because I would like to talk louder, but I feel like it will be too loud unless we turn down the gain a little bit. Okay, now I'm talking a little louder, more comfortable for me. So that's all I want to say about Bose-Einstein condensation. This is what I did for many years, and I still work in this area. But I want to talk really most of it this evening about a very different topic. I want to talk about something which is related to what happened at the very beginning of the universe. So let's see if we can go back to the very beginning of the universe. The beginning of the universe was 14 billion years ago, and at the very beginning of the universe, something was not right. Something was imperfect. And to understand why the universe came into existence, we have to understand this imperfection. We were shapen in asymmetry, and in imperfection did the universe conceive us. Psalm 51. Oh. So, there's a conference in Villa Hermosa. 14 billion years before that, this happened. It was big. It was a bang. It was a big bang. The universe was full of particles. As a simplification, I'll say that those particles were electrons and protons and neutrons, the things that make up atoms today. But also, in addition to electrons and protons and neutrons, there were anti-electrons, anti-protons, anti-neutrons. And in fact, back in those days, there was much more stuff in the universe than there is now. Many more electrons, many more protons, many more neutrons, many more anti-electrons, anti-neutrons. There was much more stuff than there is now. Most of the stuff is not here anymore. How did that happen? The universe expanded. And we learned, maybe in high school chemistry, that as you expand things, if you expand a gas, the gas gets colder. So the universe expanded, and now you can see, let's see that again. Ready? It got bigger, yes? And look, here it's red, that tells you it's hot. Now it's cooler. Still very hot, but cooler than it was. What happens? Something very romantic happens. Oops. The electron finds the anti-electron. The proton finds the antiproton. The neutron finds the antineutron. Each particle finds its true soulmate. It's sweet, isn't it? Yeah, it's very nice. Okay, but there's a little bit, we say when you have the rose, you also have the thorn, right? The married life was very passionate, but it was short. So the electron meets the anti-electron, pop, pop, pop. One by one, the particle and the antiparticle meet, and they destroy each other, and there's nothing left but photons. And this happened all around the universe. Everywhere around the universe, pop, 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 pop. You can't see the top, but there was a giant wedding. And in the giant wedding, there was somebody for everyone, almost. Because look, you see, there's everything, all these things, but look, there's an electron, there's a proton, there's a neutron. These did not find their soulmates. So the question is, can't see this is, but who are these last few lonely particles that nobody wanted? Yeah, they're you. Yeah. Sometimes I feel that explains a lot about the human condition, you know? Okay, so at the beginning of the universe, there was something which was nearly perfect. There was nearly exactly the same amount of protons and antiprotons, nearly exactly the same amount of electrons and anti-electrons. There was almost perfection, there was almost symmetry. There was a tiny difference. The tiny imperfection was a little more protons, a little more electrons, a little more neutrons. It was an imperfection, but it was a very important one, because those last, the proton and electrons stick together, they form atoms, they form neutrons, they form dust, they form stars, they form galaxies, they form planets, they form us. It was good. So this imperfection was really important, but it's also very mysterious, because usually you think if something is so completely perfect, how come it's not absolutely perfect? How come it's just a little bit wrong? We were born of this original imperfection. So how can we go back and learn more about it? There are no time machines. Back then no one took records. How can we look long ago? And we can ask ourselves, how do we learn about the dinosaurs long ago? So there are three ideas I want to mention, and all of these ideas are very much in use in modern physics and cosmology. And one of them is telescopes. This is an enormous telescope, which has not yet been built, but when it's built, it will be the largest telescope in the world. If we look at something which is very far away, like this galaxy, if this galaxy is 10 million light years away, when we see the galaxy, we don't see it as it is now, we see it as it was 10 million years ago. If we look to see the galaxy, which is the thing which we see, which is the farthest away anyone has ever seen, is 13.3 billion light years away. When the light that we see it as the universe was when the universe was only 4% as old as it is today. It's if I were to look out and I could see Eric when Eric was 2 years old. Hello, baby Eric. But that's still not nearly good enough, because this moment when this imperfection happened that enabled us to exist, that was much, much earlier. This is not far enough away, and we can't see any further back. Another idea is you could use a particle collider. You can take protons and antiprotons and smash them together in a giant machine, and it makes a very hot cloud of energy, which is not so very different from after the Big Bang. And the largest of these machines is partly in Switzerland and partly in France. It's called the Large Hadron Collider. It covers many, many kilometers. This is an aerial view. It's underground. This inside is where they use to detect the collisions. There's a person. There is a person. This is the largest scientific instrument ever built, and yet it apparently is not able to address this question. The results are coming in, and they're a little disappointing in this respect. Is there a third way? And yes, there is. Looking for dinosaurs, if we want to understand dinosaurs, we look at their fossils. This is how we understand dinosaurs. We would like to look for a fossil of the Big Bang and learn about it this way. So there are many symmetries in nature. Of course, this is a snowflake. I'm guessing there are not so many of these here in Tabasco, but tonight, actually, I've seen on the internet it is snowing in my home place in Colorado. It's snowing, so. But I'm looking at more basic symmetries. One symmetry is electrons act just like electrons, protons act just like protons. The other is basic particles look very similar to each other if you look at them in the mirror. If you look at yourself in the mirror, it's not always easy to tell if you're looking at yourself in the mirror or if looking at a photo of yourself in the mirror, because most people are pretty symmetric. Not all people. When I look at myself in the mirror, I see someone who is missing a right arm. Doesn't look like me at all. Now you can see why I'm so interested in these questions of symmetry. Also, a particle, this does not apply to big things, but if you look at collisions, if you look at interactions between particles, which are just one or two particles, like if an electron bounces off a proton, you take a movie of it, and then you run the movie of it backwards, the proton bounces off the electron. You can't look at this movie and decide if the movie is running forward or backwards. So these are the three basic symmetries that we see in fundamental particles, and they're all pretty good, except we know that matter is not exactly like antimatter. There's a little bit more matter than antimatter, and it's hard, this is now getting a little bit too complicated to describe for this conference, but there are theorists, particle theorists, who think very hard about this problem of how could there have been this asymmetry that made us exist? And when they think about these problems, they come up with mathematical explanations. And the same mathematical explanations, which explain why we are here, why there's more matter and antimatter, also predict that some of these other things must not be exactly true. In particular, they tend to predict that electrons and other particles do not look exactly the same in the mirror. So our job in my laboratory is to look at electrons and also look at electrons in the mirror, and we can compare them. Are they a little bit different? If so, this helps explain, using these extensive mathematical theories, this other very important asymmetry. We are looking our key assumption is that fossils don't vanish. Basically, the same asymmetries, or dinosaur bones, if you like, that gave rise to the universe should still exist today, for instance, in electrons. Electrons are the simplest of particles. Here's Mr. Electron. Hello, Mr. Electron. He's very friendly. It's a charge. It's electrically charged. It has a mass. It's spinning. If you take some electric charge and spin it, it becomes magnetic, so it has a north pole and a south pole. In this respect, it's very much like the Earth. The question we want to ask is it possible whether the North Pole and South Pole are exactly the same, or could they be slightly different? If you look at the Earth, the North Pole and the South Pole are really quite different. The North Pole is sea ice. It used to be sea ice. The South Pole is mountains. The North Pole has polar bears. The South Pole has penguins. If you ever see penguins and polar bears together, either you're in a zoo or someone has used Photoshop. You know, they live very far apart. So the North Pole and the South Pole of the Earth are quite different, but it's not so clear. Every time anyone measures the electron, the North Pole and the South Pole are just exactly the same. But we could imagine that they'd be a little bit different. For instance, the electron is mostly a negative particle, but maybe it has a little positive charge near the North Pole, a little negative near the South, or vice versa. If they did, this negative would add up, this positive would cancel, and it would act a little bit as if the center of the charge of the electron was not the same place as the center of the mass of the electron. These two things would be offset by some tiny distance. People have tried to measure this thing. It's called the electric dipole moment. If the center of charge and center of mass are not in the same place, that's called the electric dipole moment. It would mean the electron does not look the same in the mirror. And if this were the case, it would help explain a lot of things in physics, including this mystery I told you about. Anytime anyone has ever gone to look for this, say back in 2005, they measured this and they said, as near as we can tell, no, they're not different. If they are different, they're different by no more than 10 to the minus 27 centimeters. Is 10 to the minus 27 centimeters a short distance? It sounds short. We can compare it to the size of the electron, which is about 10 to the minus 13 centimeters. It means that the difference is 10 to the minus 27 over 10 to the minus 13, 10 to the minus 14. If the electron is not perfectly round, if the electron is offset like this, it's by a number which is, the amount is less than 10 to the minus 14. A very, very tiny number. So what we're looking for is an imperfection, an asymmetry in the electron, a fossil of the Big Bang, if you will, which is sort of smaller than 1 part in 10 to the 14. That's the experiment we are trying to do in my laboratory in Boulder, it's called the EDM experiment, electric dipole moment. This experiment I've done for many, many years with my friend and colleague, Professor Junyi. This picture of him, you can see him, he's one of the world's most famous laser spectroscopists. Here he is sort of leaning on his laser. He's looking a little dreamy. His graduate students tell me that he hates this picture, so I often try to find a way of including it in my talks. And of course, we've also had many very talented graduate students and undergraduates over the years, and here are some of them who've worked either in my lab now or recently in my lab. Kong-Kwen Ni is now Professor Kong-Kwen Ni at Harvard. Will Cairncross was very much involved in the data I'm going to tell you about today. And Tanya and Xiaobun are working on the next generation of measurements. And we thank the National Science Foundation, our standards laboratory, NIST, and actually a private person who just likes science, who decided to give some money. Thank you, Mr. Marsican. Okay, so we want to measure something very carefully, and there's a rule in experimental physics, which if you want to measure something very carefully, your job is to turn the thing you want to measure into a time, or into a frequency, because time and frequency are the things that we measure the best in physics. If you see, or in all of science, if you see a number which is measured from a scientific measurement, and it has more than about 4 or 5 digits, the answer, the number that they measured, almost surely they measured it by measuring a frequency. So for instance, here's a grandfather clock. This is a very old clock. It's more than 200 years old. And yet already, this is a very, by the standards of scientific apparatus, these are amazingly accurate. They keep time to a part 10 to the 8 or something like that. So suppose, how can we use it to measure something? There's a pendulum that moves back and forth inside the clock. Look at this advanced PowerPoint skills. See, there it is moving back and forth. Why does it move back and forth? Because of gravity. If it's over here, gravity pulls it down and makes it swing. If it's over here, gravity pulls it back. And this turns out to be a pretty good way of measuring gravity. If you measure the frequency, the time, how long it takes for this to go click back and forth, it's sensitive to the gravity, and if gravity becomes stronger, it pulls harder and it will move faster. So if we were to take this clock and move it to a planet where gravity is only, it's the same as ours, except it's 1 part in a million, just a tiny, tiny bit larger gravity on this planet, it would be easy to see the clock would tick a little faster. And this is an old clock, 200 years ago. Modern clocks can measure time, changes in clock frequencies, changes in time as small as 1 part in 10 to the 15. Actually, this is old. It's now approaching 10 to the 18. Clocks have gotten much better in the last 5 years. Partly due to my colleague Junyi, and partly due to his colleague Anna Maria Ray. Okay. Say we don't want to suppose we want to measure how strong a magnet is. This is the compass. The compass will point towards the North Pole. It rotates around. This is attracted to the North Pole. And if we put a little compass magnet that can pivot back and forth in the middle between two big magnets, it will swing back and forth. If it tilts this way, the South Pole will flip back, it will wobble back and forth. If we take this and move it and let it go, it'll go wah, 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 wah. And we can measure that frequency. And the frequency at which it wobbles back and forth tells you how strong your magnet is. We measure the frequency, we measure the magnet. So now, measuring the magnetic field is very difficult, measuring the frequency is very easy. We've converted the thing we want to measure into frequency. Actually, this is how, this is an MRI imager, an NMR machine. They put the patient inside. What is the patient made of? We know what patients are made of. They're made of protons. And so we put the patient inside. The patient's protons have North Pole and South Pole. They wobble back and forth. We measure these frequencies. That's what's going on inside one of these machines. But we're not so interested in magnetic fields. We're interested in maybe whether our electron has got a little bit of positive charge on one side, a little negative charge on the other side. So we take our magnets and we put some positive stuff here, some negative stuff here. And if the electron has an electric dipole moment, its frequency will change. We can measure this frequency with which the electron wobbles back and forth very, very precisely. That's basically how we measure the electric dipole moment. There's a problem. If the electron EDM exists at all, we already know it's very, very small. So in order to see this change in the frequency, we would like to apply a really large electric field. But if you apply a really large electric field, you get sparks, right? Lightning strikes. Zzz, zzz. Lightning comes crashing across here. There's another problem. If we take an electron and we put it in a really large electric field, and particularly pay attention, I'm very proud of this PowerPoint work. Watch this. We put the electron, we put positive charge here, negative charge here. What do we think is going to happen? Look at that. We better look at that again. That's advanced PowerPoint skills. Yeah, we can't look at it very long, right? The electron goes snapping up here. We want to look at this for a long time. So we need a very large electric field. How can we get one without sparks? I have to admit, the last time I took a chemistry class, I was in high school. So the chemistry I'm about to present may feel a little bit like high school chemistry, and if some of you are real chemists, I ask your forgiveness. Sodium chloride. The sodium is positive, the chlorine is negative. You could imagine that if you had salt, ordinary table salt, and you put an electron in between, there'd be a very large electric field between the sodium and the chloride. And that's true. The problem is sodium and chloride has an even number of electrons. All the electrons are all paired up. There's no net spin. We use hafnium fluoride, actually hafnium fluoride plus. The hafnium is very heavy. The fluorine is negatively charged. That has an unpaired electrons, and that's how we do the experiment. We actually don't use a regular electron. We use an electron inside a molecule. So the oscillation we're measuring, the frequency of the electron wobbling back and forth, is actually measured inside the molecule. So we need a very large electric field, which we get inside our molecule. And the molecule is very heavy, so even if it doesn't move very fast, we can look at it a long time. And then the other thing we need to do is compare times. Suppose we had two different clocks, and we want to say which one is ticking slower, which one is ticking faster. We could wait for 1 minute, and this one would tick 60 times, and this one would also tick 60 times. 60 is the same as 60. We might say these two clocks are exactly the same. Or we could wait for an hour, and this one would tick 3,600, 3,600, still the same. Or we could wait for a whole day, and we would find out, oh, in this case, it turns out that number 2 has ticked one more time after it's gone 86,000 times. This one has ticked one more time. This one's a little bit faster, but we had to wait a long time. Same with the electron. If we want to measure its frequency really well, we'd like to look at it for a long time. And how can we look at it for a long time? Well, we put it inside a molecule, but even the molecules, they move around too, as you know. The electrons, molecules move around. We need to keep the molecule still, so we put it in a trap. This is a trap for rabbits, okay. We don't use a trap exactly like this. Our trap is instead electrostatic. These are supposed to look like bars of metal. We put charges on these bars of metal, and there's electric fields between them, and they arrange to keep the molecule, which I represent with this green ball, trapped exactly in between these 4 bars. and they move back and forth this way and up and down, and they're trapped in these balls, and this way we can keep them around and measure the tick of the grandfather clock, or the wobble of the electron for a long time, and measure it very accurately. So our traps actually look like this. They're made out of gold. Actually, no, they're made out of aluminum, but there's gold on top of them, which makes them very beautiful, but a little hard to see because they're so shiny. But if you look carefully, you can see there's some metal bars which contain the charges that confine the particles, and they're made of polished gold, so we can collect all the light that bounces off them and use that to measure the ticking of the electrons. And this then is really the electron wobbling back and forth. It's the tick, tick, tick of the electron wobbling back and forth in the electric field and the magnetic field. It oscillates up and down. This is time. In this particular case, these are in thousandths of a second. So from here to here is about a second, and in 1 second it ticks up and down 16 times. And so the experiment we would do, well, first we ask, how do we make the electron in the molecule tick, and how do we listen to it tick? And the answer is, we use lasers. Because I'm only allowed to stand here and talk to you for an hour, and not for 10 hours, I don't have time to explain all the different lasers that we use, and why we use them to make how we can use them to measure this ticking. The laboratory we have is essentially all lasers, and way back in the corner is the experiment. This is where we keep the molecule and where we trap the molecule. Everything else is lasers. And honestly, most of the time we spend babysitting the lasers because they're very fussy. They require a lot of care and attention. But once we get them all working, we can do our experiment. Here's a vision of what our experiment looks like. Our particular molecule, hafnium fluoride plus, you can't buy this from a chemical company, it's not stable. We start with metallic hafnium. We melt the hafnium with a laser. We combine it with some sulfur hexafluoride. The sulfur hexafluoride and the hafnium react. We get hafnium fluoride, neutral hafnium fluoride. It floats down through a vacuum chamber into the space in our trap, and then we hit it with some lasers which knock an electron off, so now it becomes hafnium fluoride plus. We trap it in here. We use the lasers to make the electron tick. We use more lasers to read out the electron and to measure the electron's tick. And finally, we count whether the electron is ticking up or ticking down on this ion detector. I have swept under the rug. I've lifted up the rug and I've swept under the rug 15 years of work. It may sound easy. I'm here to tell you it's not. And I wish I could explain it all to you, but it's just kind of complicated. So this is the ticking that we measure. So a lot of the time that we spend is spent looking at these ticking and trying to understand. We see the ticking, we apply electric field, maybe it ticks a little bit different, maybe it ticks a little slower, maybe it ticks a little faster. Is this real, or are we kidding ourselves? So the first thing we do is we measure it twice. This is supposed to look like a hafnium fluoride molecule. Here's the electron, and it goes tick, tick, tick. And it's aligned like this in our trap. And then we can take the hafnium and put it down here, and the fluorine and put it up there. There it is. Now it's upside down. Let's see if we can do that again. Yeah, so we can flip it one way or the other. That changes the direction of the electric field. When we change the direction of the electric field, does the electron tick slower or faster? So we measure that ticking twice. Compare the two, subtract them. We look at the difference of those two frequencies, and then we ask ourselves, are those two frequencies the same wherever the atom is? We can move the ion around. The ion doesn't have to stay right here in the middle. We can move it a little more this way, a little more this way, a little up, a little down, a little east, a little west, just by applying some voltages, modest voltages, just a few millivolts to these rods. We can move the ion around, and as we move the ion around, we can measure to see how the frequency changes. And it's a little disappointing. As we move it around, the frequency does change. So here's how far we move it east, how far we move it west. We see the frequency change. The red is when it's a little bit to the south. The blue is a little bit to the north. So this is like northeast, and this is southwest. We measure in all these different places, and the frequency is changing a little bit in all these different places. And since we're trying to measure this frequency, you might ask, well, what's the real one? And we spend a lot of time understanding imperfections in our ion trap, why the frequency should move around a little bit. We have a very deep understanding of all the electric fields and all the magnetic fields in our trap, and these lines you see are predictions of these things. We understand these very, very well, but we spend really multiple years thinking about them. Okay. And then, once we get thinking, one understanding, we take data for a long time. We started in 2016, and we finished in 2017. You can't see this, but we took some vacations in here. We don't include the vacations, but we took data for a long time, and we plotted the frequency, the difference in the frequency, whether it's up or down. And here you can see all the measurements. And our plan is, we'll take all of these points, and we'll take the average, and that will be a really good measurement. The average of all these points will be a much more accurate measurement than any given point, some a little high, some a little low. And if you look very carefully, you might think, I think if I add up all those points and average them, they're not going to be zero. They're going to be a number a little higher than zero. Looks that way, doesn't it? Yeah, but it's not real. The computer is lying to us. And it's lying to us because we have asked the computer to lie to us. Why would we ask the computer to lie to us? I mean, the computer should be our friend. It's working. We're taking the data. It's collecting the data. It averages it out, and then it lies to us. Why would we do that? And it has to do with, basically it has to, I'm not going to show this picture. Instead, I'm just going to tell you, it has to do with the psychology of the physicist. I'm a physicist, and I like to think I'm an honest physicist. I try to do a good job. I try to make a measurement. I want to believe in my measurement, and when I report to the world my measurement, I want the world to believe in me. I think I'm an ethical, honest, hardworking physicist. But I'm also a human being. And if we could measure an electric dipole moment, which was different from zero, it would be back to Stockholm for me, baby! And I'd like to do that. Honestly, I would. I won't lie to you. And so I have an interest. I have a bias. I would like this number not to be zero. Okay, so we take a lot of data, and you can imagine what I might do. I might say, oh, you know, I don't even notice that the point is close to zero today, but I think the machine is not working very well today. Let's not include that point. Oh, here's a point which is far above zero, and the machine is looking really good. We should include that point. And I could make many, many decisions like this. All of them, I think, in good faith, but all of them may be pushed slightly in one direction based on my desires. So we tell the computer, we collect all the data, we put all the data for, like, say this point right here. We collect all the data. This is actually 20 minutes of data. We collect all the data, we feed it to the computer makes all the differences and so on, and then the computer adds a number, a random number to the data, and then it plots it. We don't know what the number is. The computer knows, and it adds the same number to all of these. So here's 0, here's 2 hertz, this is maybe 50 millihertz or something, or sorry, 0.2 hertz, this is maybe 50 millihertz. Probably what happened is it took all of these points and added 50 millihertz to it. And we see these coming in, and we don't get very excited because we don't know what number it added to it. And so all we can do is we can look at the machine, and we can try and understand if this is a day when the machine is behaving well and giving us accurate data or not. We aren't able to make the decision based on where these points are because we don't know where these points really are. This is a technique called blinding the data. Really, we say it's blinding the data, but really it's blinding the physicist. We're not allowed to see what's going on. And it gives, it's been shown many times that this gives a much better, more reproducible, reliable number. So I'm here to recommend to all the precision measurement people in the audience, you should try to blind your data. It'll be very frustrating. And we took data for all this time, and we don't know what it's telling us. And it's very, very difficult because what you want to do is go to the computer and say, I was kidding. Go ahead and tell me the number. And the computer will say, no. Honestly, tell me, hey, who pays your salary, computer? Computer says, no. We all have to get together and instruct the computer to change. So, we blind the data, And what we can do, however, is we can do statistics on the data. What is the standard deviation? Is it fitting a Gaussian distribution? We can do many, many things to convince ourselves that things are well under control. And then finally, everybody in the collaboration can go into a conference room and we can all agree, okay, computer, now we mean it. Stop lying to us. Tell us the real number. I will tell you, this was one of the most exciting moments in my scientific career because this has been a long time going into this. And we're going to zoom in. Here's everybody. We've just all looked at it. Zooming in here. Oops, went too far. The frequency measured is less than 1 millihertz, which means the electric dipole moment is smaller than 1.3 times 10 to the minus 28. It's as far as I can tell, it's 0, basically. And this is the limit. If it's not 0, it's this close to 0, which was a very, very accurate number. It was also a little disappointing. Why was it disappointing? Because, well, it was disappointing, but also a little bit of a relief, because about a year before we had made our improved measurement, a competing group at Harvard and Yale also made a measurement. Now, at the University of Colorado, we're a proud group. We're a proud atomic physics group. And it doesn't surprise us that in order to compete with the University of Colorado, Harvard and Yale had to get together. Yeah, that's right. And they did get together. And only because they got together, they did the measurement a year faster than us. And they measured a number, they measured a number which was consistent with 0, and had error bars which were 10 times smaller. And we made a measurement. We knew that our error bars were also much smaller and the same as Harvard and Yale. And so when we went to tell the computer, okay, stop lying to us, it was stressful in 2 ways. One is that if the number was not 0, this would be very exciting from a scientific point of view. But also, if the number was not 0, that means it would be very much disagree with the number from Harvard and Yale. And that would be extremely embarrassing for the people at Harvard and Yale. And we did not want to embarrass our friends. So it was hard to know what we were really hoping for. In any case, the answer was the same as at Harvard and Yale, and consistent with 0, okay. We can plot it here. This is a series of basically every time anyone's gone to measure the electric dipole moment, and they started doing this 50 years ago, they measure a number which is consistent with 0. So this is not the value, this is the error bar. This is how close we think. First they said it's 0 plus or minus 10 to the minus 24, 0 plus or minus 10 to the minus 25. The number has improved by 4 orders of magnitude, factor of 10,000 over these 30 years. And the numbers keep getting more and more consistent with 0. And the most recent measurement from Harvard, a recent measurement from Harvard and Yale, and a recent measurement from Zillow were both at 10 to the minus 28. This is significant because I mentioned before that the people who are making these calculations that are trying to predict the initial, to predict this symmetry in the universe, the imbalance between protons and antiprotons that allow us to exist, there was a theory, a famous theory called supersymmetry. And supersymmetry explained a lot of new things about particle physics, and it made a prediction that the electron asymmetry should be up here somewhere, and we're down here or lower. There were some uncertainties in the prediction, but at the same time as we were making these measurements, at the Large Hadron Collider in France, in Switzerland, they were looking for these new particles, the supersymmetry particles, and they weren't seeing them. So we think that Harvard and Yale and Gilla and NIST combined are accessories to the murder of the supersymmetric model. We are not sorry. The supersymmetric model was a very famous model, and it was everyone's favorite model in particle physics for 20 years. There was never any evidence in favor of it. There's more and more evidence not in favor of it. It had a good ride. It was flying too close to the sun. No apologies. Okay. So this remains somewhat of an open question. Just just about 2 years ago, Harvard and Yale said this. Oh, they did another factor of 10 better. And it's still consistent with 0. And it doesn't bother me so much that it's consistent with 0, but it bothers me quite a bit that it's 10 times better than our number. So we are building a new machine, and we think we'll have a measurement in a few years, maybe just 1 year, which is about as good. And that's okay. But we're also, that's actually not going to be in the new machine. That's just improvements of our old machine. We're building a new machine, and when the new machine comes up, we should be down here. Harvard and Yale could team up with Princeton and the University of Chicago and Stanford, and they couldn't get down here. Let them try. So, 14 billion years after the Big Bang, what can we learn about this original perfection? Things remain unclear, really. I should mention that this measurement in this friendly competition between Harvard and Yale and the University of Colorado is also not the only game in town. There are many other precision measurements which are trying to measure small anomalies, things which are not otherwise predicted in daily things, sort of standard things like electrons, protons, things which don't seem very exotic to the physicist, that don't require the construction of a $20 billion accelerator. This program of using precision measurement to look for anomalies, using these anomalies to predict what's going on with particle physics and cosmology, this is a big enterprise. There are many groups working on it and many different things. We can combine all these results and get an improved understanding of particle physics, of cosmology, of the question like, why are we here? How come we didn't all disappear on date night, 14 billion years ago? We don't know. That's what we're working on. And there remain, the sort of astrophysics telescope type observations, the collider, the superconducting collider measurements, and now more and more, this is a caliper. It's supposed to be making precision measurements and precision measurements looking for fossils, if you like. This is the third leg of a stool, and the stool is supposed to be explaining galaxies and particles, and that's sort of the enterprise that we're undertaking. I would be more than happy. In fact, for me, the favorite part of this presentation would be to answer your questions, so I'll stop here. Thank you for your attention.
Muy bien, amables amigos.